Okay, Algebra Qual, August 2021, rings and fields number 4. We have f of x is equal to x to the p minus 3, where p is an odd prime. We know that it's irreducible over q, and since it's an irreducible polynomial over q, we get that it's separable, so therefore its splitting field is going to be Galois. That's important later on, where I didn't specify it, but anyways. First part, determining the degree of the extension, k over q. We know that the p-3 root of 3 is a root, so if we look at that extension, we get an extension of p. And then, since it's separable, we can also get, we also get the p-3 root of unity as a root. So, and the p-3 root of unity, primitive p-3 root of unity, so it's not in q, and it's not in this guy. So when we extend it, when we extend to a field where it is there, the degree of that extension is just going to be the degree of the, or it's going to be equal to the totient function of p, which is p minus 1, because p is prime. Yeah, p-3 root of unity. So then we get the degree of the extension is p times p minus 1, which means the cardinality of our Galois group is p minus 1. That'll be coming into play in part B. Part B shows that the Galois group of k over q is neither abelian nor simple. Excuse me. So mapping roots to roots, we have two generating functions. One of them will send p3 root of 3 to c of p, zeta, right? Yeah, zeta of p times p3 root of p, and then fixing zeta p. And then the other one will move zeta p to zeta p squared, just another primitive root of unity. So that means that sigma has order p, tau has order p minus 1. If we look at the subgroup generated by tau, and we consider its index relative to the Galois group, we're going to get that it's p. This being prime means that the subgroup generated by tau is normal in G. So now we have a non-trivial normal subgroup in G. Therefore, G, our Galois group, G not simple. Okay, and then to show it's not abelian, here are two examples computed